Morning, everyone. So yesterday we started taking a look at a couple different battery designs. We talked about some of the similarities. They all need to have an anode and a cathode. They all have to run a redox reaction spontaneously. We saw the difference between the spontaneous reaction would be the discharge, is when the battery is actually running that chemical reaction so that it actually generates electrical energy. For some batteries, especially those secondary cells, we managed to be able to reverse the reaction. By putting in an external energy source, we end up replenishing some of those starting ingredients again, starting reactants. We end up being able to reuse it. Maybe more expensive at first when you purchase it, but definitely over time, because you're able to utilize it more and more, it ends up becoming more environmental and more economical with each use. We did skip over a little bit of the math, so I just want to come back and just rehash some of that there. So back to the same notes we had from earlier. We did start off with this guy here called Gibbs free energy. We talked about free energy as it's energy that's free or energy that's available for work. Really easy example of a battery is the battery is supposed to be providing your electrical device's energy. Whatever energy your battery can provide is the free energy. In that case there, we talked about here the true voltage, the true EMF from the battery here is usually going to be less because of that internal resistance, because it takes a little bit of time for the battery to act, for the electrolytes and the charges to actually travel through the background, the medium of the battery. Usually by the time we reach the terminals, the outer sides where your electrical devices are sort of hooked into, usually that's going to be somewhat less than it. In the same sense, we say, although the reaction itself was supposed to give you some true amount of energy, some of that energy here is definitely inevitably lost to heat. You notice batteries sometimes they heat up, and overall we're just interested in how much is actually available for us to do useful work, for us to run the electrical devices that we want. So we're going to come back and we're going to resketch this diagram in a little bit. Again, some key pointers that we said before we do that there. We said energy is defined really strangely. We set all energies to be negative because 0 is when charges are really far apart. In this case here, I'm not actually plotting delta G, the change in G. I'm actually plotting free energy directly. How much free energy do my reactants have? How much free energy do my products have? You notice both numbers will have negative. I think I used negative 10 and negative 50. But what we're saying is we're just saying roughly, relatively speaking, the reactants still have 40 more than the product side. So that's the energy that I'm going to be actually able to harness as free energy. We're going to mainly, in the second case here, look at this formula here. What's the relationship between delta G? So final minus initial. If I prop my reactant line over, because this line is downwards, I know negative delta G implies that this thing here is spontaneous. We're going to use this relationship again and actually get delta G here, its relationship to K, which is the equilibrium constant. And as well, with this very same delta G here, we did more so in our redox chapter, how does the delta G match up with the voltage as well? So we're going to come back and we're going to practice a few questions with that there. We get into a little bit of derivation here, and we'll end up with an equation called the Nernst equation. I'll derive this for you, but this one here is in your data booklet. And this one here, essentially just big scale here before we get into it. Big scale is, so far our tables have been written at standard state. You should be able to tell me what standard state is. So things like 1 bar of pressure, 1 mole dm cube. I have to have the most pure and stable allotrope. Temperature, surprisingly, is not in this, but we're going to just throw on a temperature of 298. That's usually what your tables are measured under anyways. And what we're going to find is, especially as the battery ends up running, we're going to steadily be losing reactants. So the amount of free energy is going to slowly decrease. We're going to be gaining products. And eventually, we're going to be at a state where the delta G is no longer negative. We now hit a dead battery where the delta G is the change is actually 0. The Q value, which is the equilibrium constant at any given time, not necessarily at equilibrium, this one here you see is going to actually subtract off the overall voltage. So when the battery was fresh, maybe it said 1.5 volts. But over time, as you run that battery for longer and longer, you notice there actually is a temperature dependence of the battery itself. We'll qualify some of these other terms. And overall, this is that same. This is the voltage that is sort of left over as the battery is running, as the proportion, as that ratio of products over reactants changes over time as the reactions occur. So more on that a little bit later, and we'll practice through a question. We'll apply that to a concentration cell in a second. There was one other formula. I'm going to actually do this one first because this one's a little bit easier. especially when we're starting to take a look at, we introduced hydrogen fuel cell yesterday, we started taking a look at, well, if the enthalpy change here is the overall, I expect it to be exothermic, I expect it to be negative, I expect this much energy to be released from the chemical reaction. That's the true amount of energy that I expected to get, and yet when you actually calculate how much of it is actually free for you to use, you actually need to subtract off how much energy is actually locked away due to entropy. Because the delta G is going to be a little bit less, we actually have some of these heats of formation, Gibbs free energy formation. We just do a ratio between how much is actually free versus how much is sort of total. I'm referring to the enthalpy as the total amount of energy. By doing that division, I mentioned yesterday, I don't really know why it's negative and negative, but based on this ratio here, the efficiency should be positive, something between 0 and 100. So what I pulled up for you here is table 12 on your data booklet. I'm just going to give you one sample reaction, and we're going to see if we can calculate this thermodynamic efficiency. So we're actually going to take a methanol fuel cell. So this was the battery right after that hydrogen fuel cell that we just talked about. CH3OH, there's a funny 3/2 here. Remember in chapter 5, we had this pesky little, everything is quoted for 1 mole, so that if I have this energy term, whether it's the heat of formation, whether it's Gibbs free energy of formation, I know that's for 1 mole. So later on, if I then apply Hess's law, if I need to scale it up, I can just multiply the guaranteed 1 mole value up or down, however I need. Now we definitely know, based on the way it's written here, we have our reactants on this side here. These are the chemicals that I need, and they're going to overall become products. So let's have a look at efficiency. Again, efficiency, I'm going to use eta for the symbol. Efficiency, they say negative delta G over negative delta H. So they want us to find what's the Gibbs free energy change as reactants become products compared to the enthalpy change. For Gibbs free energy change here, we only had one way of doing it, actually 2 ways. And one was the delta H minus T delta S. You could totally do it that way. The other way we could have done it, this guy can be found. Let's do the Gibbs free energy of products minus the Gibbs free energy of reactants. Remember, the Gibbs free energy of elements are 0. For delta H in chapter 5, we actually found 7 different ways of finding this delta H. We're not going to use calorimetry because we don't have experimental numbers. We're not going to use bond enthalpy because at the very least this methanol here is actually liquid. We actually also decide here for water state here. Earlier we said when water was a liquid or water was a gas, the efficiency was different. It's best to say for a combustion reaction that this is liquid. So I don't have the value to do bond enthalpy. I'm not given many equations, so don't do Hess's law. I could use formation numbers. That's the way I'm going to do it here. Well, since you use formation numbers for the delta G, let's do the same on this side. So the delta H, likewise, formation of an element is 0. Because this one here is a combustion, I'm not going to use the combustion method, or else I'll get X equals X. And this is not ionic, so I'm not going to use Born-Haber or dissolution. So let's just do these through separately here. Let's calculate here the delta G first. The delta G, using that formula, is going to be the Gibbs value of CO2 plus twice the Gibbs value of water, careful it is a liquid, minus off the Gibbs value of methanol as a liquid, and then added to 3/2. I know the Gibbs value of an element is going to be 0 because you can't form elements for anything tinier. Just make sure when you're on table 12, just look up the correct column here. So the Gibbs free energies are sort of down this middle column here. CO2 is near the bottom, so CO2 has a Gibbs value. Double check my numbers as we go through here. This is negative 394.4. That's in kilojoules per mole, plus twice water. I'm deciding to use water as a liquid, so there's water as a liquid here. Negative 237.1. Minus off the Gibbs value of methanol. I had trouble finding it previous, so methanol, Gibbs free energy here, the formation. So if I actually wrote the formation of methanol from its pure elements, assuming that you've done that hypothetically, they've already quoted for you, here's the free energy change based on that reaction. And here I am just using Hess's law and actually just working with the numbers. So that term I know dies away because free energy of a change of an element is 0. So crunch it all through there and we figure out what's the change of the reaction that I'm interested in right now. Plus 2 times negative 237.1, add 167. I'm getting here the change in Gibbs free energy is negative 701.6. If you're doing sig figs here, because we're doing plain old add and subtract, we're doing the decimal place rule here. We want to round it to the ones place, so this one should have been 702. I'm not quite done the problem, so I'm going to leave it that way. In terms of the heat of formation value here, exactly the same formula, except instead of using the Gibbs free energy formation values, we're going to use the fourth column, which is the heats of formation. So I'm just going to punch our way through here. We're going to use the heat of formation. It's always good to actually write out the chemicals so you know which terms that you're actually plotting over. Sorry, my color's a little crazy here. Delta HF of methanol as liquid plus 3/2. That term's going to drop away anyways. O2. And then I basically work our way through. So the formation value, this is the heat of formation this time. As a liquid, this one here is negative 285.8 plus twice the value for water. Oops, sorry, I switched those two. This one I meant to say negative 393.5, so that's this one here. The water is negative 285.8 minus off the value for methanol, so that's going to be this negative 239. And again, the other term just dropped to 0, so don't worry about it. And I crunch that through there. Negative 393.5 minus off 2 times 285.8, add 239, and I get negative 726.1. Again, for sig purposes here, you should round to the ones position. This is quoted in kilojoules per mole because this whole table is quoted in kilojoules per mole. So we already see the difference here. If you now think about exothermically here, this is the amount of energy released. You were supposed to be able to get 726 every time you run 1 mole of this reaction, and yet because some of the energy is locked away as we convert between the most random state on this left hand side here is the 3/2 oxygen, on the right hand side is 1 mole of gas. We're going to actually lose some entropy, changing sort of the look on what the molecules themselves are doing. Some of the energy actually gets locked away. So now we have it then, we can then do efficiency. Again, they have a strange negative. My only guess is they realize that you're going to actually come out with negatives to begin with, so they want you to convert it, to think about it easier as free energy, but overall when you do the math of it, the negative drops off anyways. So out of the negative 726.1, drawing those numbers a little bit smaller, keep the whole number through, 701.6 divided by this answer here, and I'm getting 0.966, so therefore we are 96.6% thermodynamically efficient. Of the 726 that exothermically gets released, we lose a little bit due to the entropy of the system. We see that when we do our formula delta G, this can also be written delta H minus T delta S. We were supposed to get the entire 726, and yet some of that energy was actually locked away, so we only have about 97% of what we have left over. So that's one calculation that they might expect you to deal with here. It's just a really qualitative way of comparing. Here's how much energy I actually have freely available for use. The more interesting formula here is with that those curves that we've been drawing with Gibbs free energy here. I'm just going to actually start off with one of our formulas. So let's just do this on the side here. So that's our first equation. Our other equation in deriving the Nernst equation, we're going to start off with the equation that we saw back in chapter 7. And it was this relationship between delta G was actually quoted as negative RT ln K. So we know delta G here. This one here is the change in free energy. Careful when we plot those graphs here, we usually plot it just straight free energy. To do the change, we still need to compare final minus initial. The R here is going to be the universal gas constant, so 8.31 joule per Kelvin mole. The temperature here, make sure it's Kelvin, so we're just going to put in 298 Kelvin. And then we have a ln K. This K here is actually your equilibrium constant. So if you think back to your chapter 7, your equilibrium constant here, we called it Kc at that point here. Kc was actually a comparison between the concentration of products over concentration of reactants. The main thing I want to emphasize in this formula before we punch it through a derivation here is the fact that we know we want delta G negative to be spontaneous. Because in the formula there also is a negative here, a negative, that means this term here, the K, actually has to be a big positive number. Something bigger than 1. And that way, the delta G overall can still be negative. If the K is somewhere between 0 and 1, it becomes a negative ends up becoming positive, and therefore we're going to be actually non-spontaneous. So something actually bigger than 1. So what we're saying sort of in words here is the more spontaneous something is, the more negative the drop in free energy, the more that I have available for use before the battery dies off, the more to completion it gets. In fact, in this case here, this formula that we've been seeing is actually a slight simplification from a little bit longer of an equation. So I'm just going to show you the longer equation. So delta G here, to factor in the fact that we're not always going to be at standard state, we still will have this term here, negative RT ln K, but the the longer equation here is actually plus RT ln Q. So they actually factor in, well, this battery here steadily over time is going to be dropping in concentrations. It's not always going to be K here. So in this case here, I'm just going to remind you, this Q here, we sometimes called it a trial K. And basically this one here was the equilibrium constant at any time. Usually when we did those ICE tables, we used the initial values. We compared, is my ratio right now too big or too small to figure out whether it shifts left or shifts right. But that's what we're doing for that Q here. In fact, with that derivation here, you can actually, this is just on the side, you can actually convert this one. When you do the subtraction, you can actually pull out negative RT. We can go ln. I would have done a minus of a minus like this. And whenever logarithms are subtracted, we can actually go K over Q. So just to prove to you, well, like how did we end up with this equation that we saw in chapter 7? Well, what if I was at equilibrium? If I'm at equilibrium, the Q is exactly going to be K. K over K just becomes 1. Ln of 1 just becomes 0. And therefore, I have delta G equals 0 when at equilibrium. So even though it's a more thorough equation here, at least it's more consistent. So I'm just going to plot a graph of this one here, and then we'll show you how we're going to manipulate through here. Again, the graphs are a little bit weird to understand because, again, what we're plotting is just free energy. We are not plotting change in Gibbs free energy. This is just the free energy. We have that funny thing that when charges are at infinity, we call that 0. That way all our energies end up being negative. We're going to have reactants over here, products over here. I'm plotting against our reaction coordinate, or against time if you like. Let's say I use that example again. Let's go from negative 10, and let's say products are negative 50. Right? That's the actual free energy that the chemicals themselves have. In this case here, I would imagine I start off with a lot of reactants. What this formula says here is, first thing, the delta G is negative. The delta G in this case here is negative 40. The negative tells us already spontaneous. And just like I mentioned here, the more negative this is getting, it means the K value is bigger. It means this product over reactant ratio here is larger. That means the equilibrium position is shifted very, very far along to the right-hand side. So if you plot a graph of this one here, at first our battery does something like this. And what we're going to see here is whether we are pure reactants or pure products, we will have a delta G negative. We will spontaneously go to what's referred to as an equilibrium position. And the equilibrium position here, this is just generalization here, mixtures are always, mixtures have the highest entropy. And we knew in, thermodynamics second law here, we knew that things tend towards the highest entropy, highest randomness. So imagine making a mess full of only reactants or only products. The second that you have a mixture of chemicals, even if they don't react, you can make more of a mess. So what's going to happen here is we will naturally have delta G less than 0. We're spontaneously going in that direction. It's just that overall, our big delta G, which is negative 40, because this is a very negative number, this equilibrium lies really, really close to just having pure products. So we say that reaction, pretty much the wording here we can say goes to completion. And again, in sort of numbers here, we can say it approaches 100%. It's practically like I don't have any reactants left. Again, that's a picture when the battery is fresh. What if I've run this battery here for a week or 2 weeks or a month? Over time, then, I would imagine my reactants are steadily decreasing. I don't have as many of them. So although the reactant molecules themselves are supposed to have, let's say, negative 10 as free energy, because I have less and less of it, the free energy total actually drops off. Because I'm gaining products here, I know that was the less free energy side here, but I have more of that chemical there. This free energy here actually does increase. And I'm going to eventually reach a situation where my big delta G here is actually no longer going to be negative, which means this one here is no longer pushed over to 100%. The curve here instead is going to look something like this. And in that case there, in the brown that I'm drawing here, we can say after use, the delta G drops to 0. And when that delta G drops to 0, I don't have as big an impact on this K anymore, pushing it over 100%. We're going to find this equilibrium actually shifts over somewhere in the middle, although not necessarily going to be 50-50 because of the coefficients in the balance equation. So we're going to still, well, delta G is 0, am I spontaneous or not? Well, it's sort of like I go forwards. It's sort of like I go to products, but I really have no net tendency to end up going forwards anyways. So that's the picture I'm thinking about here, going from a fresh battery to a dead battery here. If I have a fully dead battery and I need to recharge it, what I'm actually needing to do is I'm actually needing to run the reaction the opposite way. So for the recharge cycle here, maybe I have a dead battery. I'll plot my free energy against our reaction again. This time I'm going to plot products to reactants. Right? I want to force the reverse reaction, force the products back into reactants. Unfortunately, in this case here, actually might be easier. Just let's keep constant so that you can get a sense of delta G, products minus reactants. So in this case here, what I'm saying is either the free energy reactants has matched up with products, or it's even possible that the reactants even have lower free energy. I don't have any reactants left over, or I have all of it as products. It's possible this curve here is actually swap places. So in this case, when we plot the line over, I plot out what delta G is. The delta G here is a big positive number. Let's say it's positive by 40, just for argument's sake. And in that case, when you use the formula again, delta G is supposed to be negative RT ln K. If this one here is now a positive value, we're going to find K has to be relatively small. Still has to be positive because it's a ratio between concentrations, but what we're going to find is between 0 and 1. It actually means, in the interpretation here, reactants are favored. So in this case here, based on my reactants, I don't have a lot of them left. It's going to both sides are going to fall, but you're going to notice that equilibrium position that I fall to, it lies really, really close on the reactant side. So at the moment, without actually supplying any external source here, this one here, pretty much no reaction, pretty much 0%. Right? And what we're going to do here is we're going to plug into a wall. We're going to actually supply an energy source. I know it has no desire to go the other way, but what we're going to do is we're going to use the external power source here. We're going to force some of these products back into reactants. As I gain more reactants, this side replenishes here. I have less and less products, and gradually over time, I'm going to have my curve shift the other way again, and we're ready to spontaneously generate more voltage. So that sort of fleshes out the relationship between the delta G stuff from Chapter 5, enthalpy, free energy, and Chapter 7 with equilibrium. There is one other equation here fleshing out here. Delta G can also be related to the voltage. So let's just take a look at that expression here. The delta G is also, I think this is also on your formula sheet here. There's also this negative again, it flips a sign. The other way of looking at it here is it's also related to the standard voltage. So for example, if I want delta G to be negative, that's spontaneous, that's when my battery works, the N is going to be moles of electrons in your balanced redox equation. So there is a little bit of balancing there for you. F is called Faraday's constant. So Faraday's constant, we usually just round it to 96500. That's going to be charge per mole of electrons. So the figures out, if I line up an Avogadro number of electrons, each electron here has an elementary charge, so 1.6 times 10 to the negative 19 coulombs. I multiply the Avogadro, and I roughly get this Faraday's constant, so that if I have, here's how many moles of electrons, per mole of electrons, here's how much charge it is, I'm going to then take, this one here is a net charge of all my electrons. If I take charge, and I multiply the E naught, this one here is my voltage. You can work on the math for yourself here. Charge times voltage actually gives you the energy. If you remember from yesterday's lesson, we had defined, well, voltage was defined as energy that's given per charge. If I want to just isolate for that, then the energy is going to be the Q, charge times the voltage. Right? So at least all the units at least are consistent here. Mainly I'm interested in sign for this case. So I want delta G here to be negative. Because there is always this pesky little negative in the formula, the mole of electrons is going to be positive. Faraday's is positive here. That means this voltage here also needs to be positive for spontaneous. So we now have two relationships in looking at whether the reaction will be spontaneous or not. One is looking at the K constant. If the K is relatively big, if this ratio is relatively large, the delta G will be negative. The other way that delta G can be negative is if the voltage is very, very positive. So let's go back into that more thorough version with that negative RT ln K. We're going to do a derivation here by actually plugging in this NFE kind of concept. So let me just do this back on the side here. So starting off, we're going to go, this is the formula I wrote for you earlier. Delta G is actually equal to negative RT ln K plus RT ln Q. You'll notice sneakily here, I've actually dropped that not symbol. This one here is now for any condition. Sorry, this one here is not standard conditions. So it's just free energy, and because we're not standard, I'm not just going to be considering at equilibrium or just one quantity. I want to know, well, what are my non-standard conditions? What's my ratio at this point here? And here at this point here, I know this negative RT ln K, if it actually is equilibrium constant, I know that one there is at standard conditions. So that's going to be non-standard. This is going to be the standard free energy change. And now all we're going to do is we're going to punch in this last equation. If delta G is also worded as negative NFE, I can actually punch in, well, this side is going to be negative NFE non-standard is equal to the standard position, negative NFE naught, and I still have this pesky little plus RT ln Q. So I'm just trying to work from that equilibrium understanding. I'm trying to factor in this sort of redox relationship. What you're going to do here is we're actually going to divide everything by negative NF. I don't want to see all this negative NF around. And we're going to get our final equation here, the E, which is a non-standard condition, non-standard voltage. So the voltage of the battery at any given time is actually going to be the E naught. This is the standard voltage. This is when everything is at 1 molar. That's what we're used to for standard conditions. But there is a correction term here. We're going to have because I divide by negative, so it's a negative RT over NF ln Q. You don't need to do that derivation ever again, but we just give this equation a new name here. We call it the Nernst equation. And essentially, the Nernst equation is a way for you to mathematically compare the standard voltage that we get from our table versus the voltage at any point. We defined a lot of these terms here. The R is the gas constant, I had said earlier, 8.31. And the temperature here was the absolute temperature. Usually it's going to be 25 degrees, or it's going to be 298 Kelvin. So let's just practice a quick question here, just so that we get a sense of how this Nernst equation actually applies. Let's go back to a simple redox equation. So zinc reacts with copper 2 plus, becomes copper, and it becomes Zn plus 2. At standard conditions, so I'm just going to rehash here. At standard conditions, like I mentioned, the ion concentration should be 1 molar, 1 molar. That's where all our tables have been worded. So what you can do is you can go to your table, you can break up the half reactions, you can say, well, Zn is supposed to become Zn plus 2, that drops off 2 electrons, the copper 2 plus picks up those 2 electrons to become copper. We can go to our trusty table here, zinc doing our oxidation, so this one here is zinc, if I can find it, so zinc, and going the opposite way here, this is written as a reduction potential to negative. If I flip it, it's going to be positive 0.76. So positive 0.76, that's an E naught. Copper 2 going to just copper solid, so that's going to the right. This one here is positive 0.34. When we get the net voltage, I just add those two voltages together, 0.76 plus 0.34. This gives me here 1.10 volts. But again, the emphasis here is that is at standard conditions. Let's say that's my fresh battery when I happen to have 1 molar copper ions. But let's say this battery here has been running for a little bit here. Let's say the concentrations are no longer the same. We did this a little bit during our lab here. Once we had our voltaic cell set up, we were asked to, well, let's add water to one side, add water to the other side. What we ended up seeing was, because these things here in the background, because all of these are equilibrium reactions, what we can do is we can end up affecting the equilibria. So for example here, if I have the two sides of the container, if to the zinc side here, I end up adding a bunch of water. If I add a bunch of water, the zinc concentration goes down. When I pull that concentration down, it's going to shift this equilibrium to the right. It's going to end up generating more voltage than this one here. If it was just producing 1 molar, I get 0.76. Now I'm going to produce 1.5 molar, 1.9 molar. It's going to produce more than that. In a similar fashion, if I took the copper side, if I added water to that there, if I end up diluting it, that goes against me. If I dilute it, it pulls the equilibrium back to the other side. It doesn't let as many copper ions go forward. I'm going to get less voltage there. That's still just sort of shifting equilibrium, right? Changing voltage. What I'm interested in now is I'm interested in what if I actually have been running the battery for a little while. So what if this one here was, I know right now here is starting off at 1 molar. Let's say as I run the battery, let's say this guy here, so that's, let's say part A. Let's say part B, instead of adding water to artificially just shift the equilibrium over, let's say I've been running the battery a bit so that the copper concentration, I'm just going to totally make up numbers here. Let's say the copper drops to 0.1 molar. And the other case here, let's say this one here, Zn plus 2. Let's say this one here has gone up to 1.9 molar, right? So sort of in the background, we sort of know there is a little bit shifting. I know the voltage is not going to be matched up with what is in the standard state. But in this case here, because I'm interested in calculating the voltage at any given point, here's where your Nernst equation comes in. So your Nernst equation, you can just copy it from the data booklet. E is equal to E naught minus RT over NF ln Q. And just careful in this formulation here, my Q is the equilibrium constant, products over reactants. The products is just going to be the zinc concentration, reactants is just going to be the copper, because the other ones here are actually solid. It doesn't matter. So those aren't included in the equilibrium expression. In the balance equation, there are 2 electrons being transferred, so we actually punch in a 2 for N. So let's do this voltage. What's the overall voltage now that the battery has been running for a little bit here? Well, at first, I started with 1.10. I minus off an R value, 8.31. 298 is my temperature. N is 2 moles in the balance equation. F is Faraday's constant, 96500. Ln of right now, I would have expected 1 over 1 for standard conditions, but now my zinc has actually gone up, 1.9 divided by copper, which is actually 0.1. I'm just going to type in this latter part for you here. I don't think this is a very big change. 8.31 times 298 divide 2 divide 96500 multiplied by the natural logarithm of 1.9 divided by 0.1. It really is just a ratio between the products and reactants. We notice based on this Nernst equation here, 0.0378, and therefore my voltage is a little bit less. 1.1 minus this answer, my voltage is 1.06 volts. So you see that based on my ratio here, it looked like I actually have, I have 10 times less copper and way more zinc. It really is this overall ratio of Q, whatever proportion that gives you, that's going to tell you what the correction term is, and that's always going to detract away, take away some of the voltage that your standard cell should have had. To sort of visualize this a little better here, what you can actually plot, if you look at the Nernst equation, it actually helps compare for us the voltage, so E with no naught symbol, so the voltage at any given time, I'm going to plot it against ln Q. So I'm going to plot this E here, but I'm going to plot it against the X value of this ln Q. In this case here, when will this E exactly equal E naught is when this RT ln Q term exactly kills itself off. That's when ln Q actually, the Q value would actually be a 1. The ln Q would actually be 0. So therefore, if I'm at 0 as a ln Q, I should find this graph here lines up at 1.10. I'm at a position here where my ln Q term is actually some positive number. Sure, it gets rescaled a little bit, so I'm going to get knocked a little bit over. So my ln Q may be some positive number, and based on the correction term here, now my overall voltage of the battery is 1.06. And as you run this battery here for longer, this proportion difference here changes even more. This voltage here will eventually drop to 0. As long as your voltage is positive though, so this is positive voltage, it still implies the spontaneous reaction. This battery will run spontaneously until it's a dead battery, until the voltage is 0. As the voltage here ends up dropping down into the negatives here, that would then be negative voltage. And again, we know negative voltage here is definitely non-spontaneous. In fact, it's the reverse reaction that's spontaneous. It's going to just bring us back to, in this case here, a dead battery. That's when things are actually fully at equilibrium. Based on this diagram, though, then that means, so standard was nice. 1 molar is a really common concentration I can use, but I can actually work out this Q ratio if instead I actually have more copper to begin with. Instead of dropping the copper from 1 to 0.1, let's say I started off with 10 molar of it. If it managed to be soluble here, I could have that correction term. I could actually get voltages that are actually higher than the standard voltage as well. That's when ln Q actually is a negative. If you minus a negative, it ends up giving you a bigger positive voltage. So that's how you utilize the Nernst equation. It basically compares the voltage at standard state and its a correction term for as the reaction proceeds. We can actually utilize this in something called a concentration cell. So it's just a nice application of it. So concentration cell. A concentration cell would be something that looks like this. So with my concentration cell, I'm going to still have a voltaic cell. I'm going to still have anode and cathode. But curiously here for my concentration cell, I'm actually going to use the same electrode on both sides. So let's say I have a zinc electrode and a zinc electrode. The potential reactions are zinc 2 plus here. I still hook up the voltage here with the salt bridge. Okay, that's a concentration cell because we're going to have the same electrodes. So same material that makes up the metal plate. Same electrodes in the same electrolyte, the same solution. But the difference, why they're called concentration cells, but the two sides here will have different concentrations. Okay. So for argument's sake here, let's say when I actually made these cells here, the solid I can't change the concentration. It's constant composition, I can't do anything there. But at least the zinc solutions, standard state here would definitely just be 1 molar, 1 molar. Right? In some sense, it's boring. But what I could do is I can say, well, what if I decided to start off, I want this concentration cell here to be 0.220 volts, molar. And this one here to be half the concentration, 0.110 molar. Right? So this is what I would imply at standard state. That is important for us because that's going to give you E naught. But what if my real cell, my actual cell, my non-standard conditions happen to be this? What we want to do is we want to figure out, is there going to be a voltage that's generated? So we're thinking Nernst equation. E is equal to E naught minus RT over NF ln Q. You will notice you do actually need to find the E naught. So that there's no escaping that part there. We need to see when zinc gains 2 electrons becomes zinc, or on the other side when zinc actually releases off zinc 2 plus and releases these 2 electrons. You can look up the numbers if you like, since I have them up here. Let's go for it. So zinc in oxidizing, it is positive 0.76. The reduction is negative 0.76. So this is negative 0.76. This one here is positive 0.76. No real surprise here because we're doing the same cell. The E cell overall is 0. And this will be true for all concentration cells here because it's the same electrode, same electrolyte. There's no difference. However, this time, because I'm not at standard state and because this ratio here isn't exactly equal, I can see what this correction term ends up being. Again, it's not expected to be much, but it does actually give me some voltage at this point. So I'm going to figure out here negative R. I'm going to show it to you with the units just so that you can see that the units cancel out, joule per Kelvin mole. Temperature is going to be 298 Kelvin, so at least the Kelvin cancels out. Divided by N, which is moles of electrons. So in the balance equation, I have 2 moles of electrons. So 2 moles. Faraday's constant here is 96500. It's the coulombs per mole. So those moles there cancel out. And then we end up with a ln Q. The Q is supposed to be, well, we need to actually decide, well, which side is actually anode, which side is going to be cathode when it's the same on both sides. Here we're going to use Le Chatelier here. If you have potentially the same reaction, the zinc could have reduced on both sides. We're going to find that the side that happens to have the higher zinc, because this would have shifted the equilibrium over, we would say the side that has higher zinc concentration will do reduction, right? Because that's what we see from the equilibrium. If one side here is 0.22, it's double what the other side is. The higher zinc, relatively speaking, it's going to shift the equilibrium to the right. It's going to allow the reduction to occur a little bit easier. So if that's going to be the reduction reaction, so the reduction occurs here, that makes this one here the cathode. So although the although the balance equation looks exactly the same, we need to see that, again, the balance equation, let me just actually write it out. So for this reaction here, when zinc runs into Zn plus 2, becomes Zn plus 2, there is no net reaction. However, we remember half the reaction is occurring here, half the reaction is occurring here. So it's actually at different sides. But we're going to see that the reduction, where I'm going to put the 0.22, the 0.22 will actually be the higher one that's actually doing the reduction. So this is 0.220, whereas this one here is the 0.110. So when I try to do the ln Q, it's going to be 0.110 divided by 0.220. Let's just crunch our way through there. Again, I'm not expecting a huge correction term, right? That's equal 8.31 times 298 divide 2 divide 96500. So just the first part gives you 0.01283. The logarithm of basically half. I just want to emphasize this notion. It is just a ratio between the leftovers, negative 0.693. And you multiply those two, give or take a little bit of rounding. I'm getting a voltage of negative 8.893 times 10 to the negative 3. So I am getting negative 0.00, let's round it to 89 volts. Right. So where otherwise your standard cell here, well, it's the same electrode. Why would I be getting any voltage? Because we are not at standard conditions, we actually do have some net voltage. Some applications of these concentration cells here, we can actually utilize them for dissolved oxygen sensors. So if instead of the zinc cell I talked about, if I can sample how much O2 is actually in the water, even if there's a slight difference in oxygen on both sides, that generates a little bit of voltage. I can have a meter that's sensitive to these really minor voltages. That's like 8 millivolts here. I can use that for a dissolved oxygen sensor. That typically is used to track sort of causes for corrosion. So it causes corrosion. Just that small amount of voltage, doesn't take much, allows that slight difference will cause some voltage to it. The other more interesting case here is we actually define pH meters. pH meters or pH sensors, they're actually sensitive to both, sure, concentration of H+, right? The more acidic, the pH drops, but it's also sensitive to temperature because you see that from the Nernst equation, there is always this temperature dependence in the formula as well. So not only sensitive to the concentrations on both sides, it may really well be H+ in the electrode, H+ in the surroundings, but depending on the proportion of products over reactants, the pH meter can be sensitive to that. Although you do need to calibrate this every time, you need to basically tell the scale, I want you to read pH 10 for this buffer solution, read pH 4 for this buffer solution, and then it'll rescale your graph for you. So I'm just going to leave you with one question here. Just in practicing the Nernst equation, not a huge section, but it's a nice sort of correction term. I'm going to use the standard cell notation. So standard cell notation. If you remember, standard cell notation is if I know which one is the anode, I'm going to put aluminum as the anode. The solid line means a change in state. So aluminum, this one here is the anode, this one here is the electrolyte. The 2 bars actually means it's a salt bridge. I'm going to have iron plus 2 here, and this becomes just iron solid. This one here is the cathode. You're going to start off doing the concentrations. Let's do standard first. So standard means I can check the table. I have 1 molar of this solution, 1 molar of this solution. But what I'm more interested in here is I actually want you to calculate the non-standard, just the E with no not symbol. When, let's do the concentration of Fe plus 2 is 0.1 molar, and the concentration of Al, this battery has been running for a long time. They both started off perhaps at 1 molar, but maybe I only have 0.0001 molar of the Al plus 3. So let me just hint at what you're going to do. First thing you need to do is you need to just balance the equation. So because this is the cathode side, write the equation iron and 2 electrons becomes iron. The other equation is going to be aluminum, loses the electrons, Al plus 3 and 3 electrons. Here you do need to balance it, so lowest common multiple, 3 times that, 2 times that. So overall your equation is going to be 3Fe plus 2 plus 2 aluminum ends up making 3 Fe. And then we have 2 aluminum plus 3 on the other side. Remember, our voltages, our E naughts that we can get on the table are already per electron, so these ones here don't change. Figure out what the standard E cell is overall, just add those two there. In the balance equation, I would have multiplied this equation by 6. When I use the equation, Nernst equation, E is equal to E naught minus RT over NF ln of Q, the N is actually going to be 6 electrons, because in the balance equation, we're actually transferring 6 parts. You have all the other values here. Careful when you're doing this Q here. This Q is supposed to be products over reactants. Again, we're just looking at the aqueous states here. Because there are coefficients in this one here, aluminum to the square and iron to the cube. So make sure you factor that in before you punch your way through Q. Take a logarithm of it and then see what you get for the voltage. If I did this properly here, I think I was getting 1.26. Right? So if you have any questions, just let me know, and we'll go from there. Thanks, guys.